Okay, so now let us start in detail with nucleophilic aromatic substitution reaction belonging to the first class, that is bimolecular displacement reaction. Let us see few examples of the compounds which will give you this bimolecular displacement reaction, and as the name indicates, it is a nucleophilic aromatic substitution reaction wherein your halide is getting replaced by the nucleophile. So if we consider the first example, here I have my nucleophile as OH minus, and thus this nucleophile is going to be replaced for the Cl in the reactant, and the product that I am getting here is 2,4 dinitrophenol. Similarly, for the next nucleophile, I will have a product which is 2,4 dinitro-aniline. Similarly, here I will have a product where OC2H5 is my nucleophile and I will have my NO2 groups at place. Just to revise what we have seen before is bimolecular displacement reaction is possible when especially I have an aryl halide which is having a substitution. That substitution is electron withdrawing substitution, and to be precisely that substitution is present, or that substituent group is present at ortho and para position. Since all these three conditions are matching, 2,4 dinitrochlorobenzene is giving you a bimolecular displacement reaction, and thus is accordingly reacting with NaOH, it is reacting with NH3, it is reacting with sodium ethoxide, and it is giving you the corresponding product where your halide portion is replaced by respective nucleophile in that particular example. Now the next question is, we have seen, or rather we all have accepted, that it is only when my aryl halide is substituted it is going to give me a bimolecular displacement reaction, or when my aryl halide is occupying ortho and para positions with the electron withdrawing group, it is going to be a good candidate for a nucleophilic substitution reaction. So now let us see all these different examples which I have already written down here. Just try to solve them and then try to probably answer why I need to have electron withdrawing group, why I need to have its position very fixed as an ortho and para, and what if I don't have those substitutions at all. So as you can see here, the first component to start with, I simply have a chlorobenzene. Second component to look into, I have a nitrochlorobenzene, para-nitrochlorobenzene. Third candidate, I have ortho and para, both the substitutions with the nitro group and the chlorobenzene. And then lastly what I have is 2,4,6 trinitrochlorobenzene. Now if I have to write the reaction, or if I have to write the product for each of this, the product per se prediction is very simple, because my Cl is going to be replaced by the corresponding nucleophile. As I can see, everywhere I have used same nucleophile as NaOH. I will have my chloro group being substituted by OH. Let me write down this particular product and then we will discuss all those reaction condition aspects which are related into it. So what I have done in all these four reactions is, I have replaced Cl with the nucleophile, that is OH. Now I want you to observe these reactions as far as the reaction conditions which are written on the arrow. If I just consider aryl halide, I have my reaction conditions comparatively very stringent, where NaOH is used at 350 degrees Celsius and at the high pressure. The moment I substitute that aryl halide with the NO2 group at the para position, I have reaction condition as 160 degrees Celsius and 15% of NaOH is used. Next is ortho and para, both the positions are substituted and the reaction temperature conditions are little milder. And in the last reaction, if you observe, when I have 2,4,6 trinitrochlorobenzene, the reaction simply occurs just in the presence of water, and warming the reaction is sufficient to give the product. So as I move down from aryl halide to tri-substituted aryl halide with the nitro group, no doubt, what I can see is the reaction conditions are getting milder, indicating that for a bimolecular displacement reaction to occur, chlorobenzene is absolutely not a good candidate because the reaction is not favorable. The reaction is forced to go to completion only when the stringent reaction conditions are utilized, and thus chlorobenzene is giving a nucleophilic substitution reaction and getting converted into the OH, but only and only at the high temperature. Whereas the last point which we all have seen, the nucleophilic aromatic substitution reactions, especially the bimolecular displacement reactions, are favorable enough when you have aryl halide attached to the electron withdrawing group and that position of electron withdrawing group is ortho and para, then it makes a good candidate for the reaction to occur. And thus, as you all can see, when I have para-nitrochlorobenzene, the reaction is taking place easily. When I have two nitro groups present on the ring system, ortho and the para position, the reaction speed is still enhanced, or rather I should say not in terms of speed, but the reaction conditions which we all have written down are still the milder. And in the third case, since all the positions are occupied by electron withdrawing group, the reaction is really feasible. It takes place at the room temperature, and not even a strong nucleophile but a simple water molecule is enough to give you the product. So this particular table indicates what? This particular table or this particular sequence of reaction indicates that when I have electron withdrawing group present, and when that electron withdrawing group is occupying ortho and para position, and as the number of electron withdrawing group present on the aryl halide goes on increasing, the reaction conditions become milder and it makes the candidate favorable for the bimolecular displacement reaction. So definitely our next point which we are going to highlight is which all such electron withdrawing groups make this reaction favorable when they are present on your aryl halide, first point. And second point is why we are considering constantly only ortho and para position, why we are not considering the meta position at all. So now we'll go into the details of mechanism and we'll try to address these two particular questions. But before actually going into the mechanism, let us first see which all such electron withdrawing groups that we all can have on the aryl halide, which will give you this bimolecular displacement reaction possible. We all have considered only the NO2, but apart from NO2, you may have other electron withdrawing groups which are present, and those electron withdrawing groups will include this. It may be your CN, it may be your SO3H, it may be your COH, it may be your CHO, or it may be your COR. All these are the electron withdrawing groups are possibly give you bimolecular displacement reaction which is feasible. What we all have written is only with NO2, but instead of NO2, any of this, if it is present, which is an electron withdrawing group, it will make the candidate favorable for bimolecular displacement.